Hello everyone, I am Bradley Sward, Associate Professor of Computer and Information Science at the College of DuPage in Glen Ellen, Illinois, and this is a well-involved example problem today of looking into status flags, data-related operators, indirect addressing, jumps, counter control loops, and Irvine library functions. Read that as well as I can read too. And so I have an example problem today to do, and I'm going to show it off first in C++. And so we're going to go through all the nitty-gritty details, and then we'll do all the nitty-gritty details as we transfer this program and we translate it from C++ into x86 assembly language. So here is my program. I run it, and all that is print out the word demo. And I could just use one cout statement, but what's the fun in that? We're trying to go low level. We're trying to understand what's going down, what's happening at the lowest levels, and just writing one cout statement is not going to cut it. So let's just take a look here. So I have a global variable called word that has demo, and what's interesting here, the first thing that's interesting, is you mouse over this thing and it says char word, and there's a 5 in the square brackets, which means that there actually is 5 characters to this. You're like, well, it's a 4-character thing. I put a D in here, put an E. Oh, I should have centered this. I'll center this in a second. The demo. At each individual character, each individual byte is storing one character of the demo. But what's happening here, the null terminating character, the actual 0 ASCII character, is sitting here at the end. Whether we like it or not, the compiler puts it in for us. Isn't that that's the reason why we have tools that do these things for us, so we don't have to think of these things. And what is word? Word is an array, a character array, but at the end of the day, any array, like the variable itself, is just a pointer to whatever memory location. I'm just going to make a nice, easy number, 612. I'm going to center this as well. I should have done this. But I'm saying, so let's just say somewhere at memory 612 is the letter D, and then every character from then on will be one character, removed from that. And this is the memory address. And again, the memory addresses will change execution to execution. Most, more because the operating system will give this program a different place in memory. But when it comes to offsets and things like that, you will see that they are very similar, and we'll see that when we get over to assembly language. So just to say 612, 613, they're all contiguous. It's a contiguous block of data with a null terminating character. And now I have a character pointer called character, and it's equal to word. And this works again because this character, this word, is a character pointer to the start of the memory where this is. So what goes in here, a D doesn't go in here. Center everything, get it done with. A capital D doesn't go in here, but since it's a pointer, a memory address goes in here. So the number 612 actually goes in here because that's the memory location where word is in memory. So just getting started here, that is how our global data is stored. And I'm not going to get into more detail about how things are stored contiguously or not or whatever, but we're good to go with the globals. So now coming down here, there's no easy way to do this kind of stuff. I'm using this as a register. I can't just use ECX without defining it. So I'm saying I'm going to put a 4 in here. And I'm using that so that I can print out each character individually because there's 4 characters. And we described there's 5. If I use a cout in C++, the null terminating character is the way that I know that I'm done printing that string. And you're going to have to do this manually in assembly language. Otherwise, things are going to go wrong for you. So 4 is going to store ECX. And this loop here, this while minus ECX does not equal 0, you will see this plays directly into the loop instruction, the loop operation in x86 assembly language. But what are we doing here? Let me just say, if this is our output, what are we doing? I'll just output. I could do that. And then put a box here and center that box and say, okay, so what is going on here? And I go, well, print out star character. And so that you need that star, what we call dereferencing. 612, you're not going to print out the number 612. It doesn't mean anything. But what this means is I know I have a pointer. Character is a character pointer. And it means go to that memory address and get me that information. So 612, go to 612, get me that D, and then print it out. So the output here will be the capital D. And then as you see here, plus plus character. Increment this guy to make it 613. And then say while, and then this is minus minus ECX. Do the decrement first. Is ECX now equal to 0? And it's no. So we're going to do this again. And so now go here, print out star character, go to 613, get me this. Add this to the output. Go over here, add to this 614. Go over here, decrement. You can see I'm going to do this 2 more times or 3 more times. And so decrement, and then go, are you 0? Nope. Okay, continue again. Go to 614, print out that character. There's my M. Increment character. This becomes 615. This becomes 1 on the decrement. Are you 0 yet? Nope. So come back around one more time. Go to 615. Print out that character, increment character, and decrement. And now you go, hey, is ECX 0? And you go, yes. And we fall through. We print that new line character. And now the program pretty much ends. And the output is demo, the 4 letters of the word. And we're not worried about the null terminating character. We're not even really going to worry about it in our assembly language example. But there are Irvine library functions and so forth where a lot of times you're going to need that null terminating character. Otherwise, things aren't going to print correctly. So that's how we're going to do things in C++. And now we're going to do, we're going to do our darndest here to make sure that we convert this as efficiently as possible into assembly language. Okay, so I've changed over my environment here. Now I'm working in the ASM Visual Studio environment using the Irvine library. And so I've moved over the C++ code so we can see it. I've kept this all the same. And so now we can set up our 2 global variables here. And so word is actually a keyword. So I'm just going to call it, I'll just call it demo. I'm going to forget I did this, but that's okay. And then I'm going to call a character is a byte in assembly language, and I'm going to put demo, and then I don't have to, but I should put the null terminating character here as a comma 0, because that's what C++ does. So we're trying to emulate what C++ does for us, and that's pretty much setting up that first variable. And now just to figure this out, if I move into the EAX register, the offset of demo, and I call write int, or maybe write hex. Write int. Let's see what comes up. I get this number 421888880. Let me see what happens if I put this into hex. I'm expecting a specific value here. Yep, that's the value I'm expecting. 004060000. Every time you run this program, you will see this because this is an offset, like I've described earlier. Every time you run your program, the operating system, Windows in this case, will give me a different place in memory to run the program because the memories are, memories coming, memories going, newing and deleting. The operating system is managing all my gigabytes of RAM. But what is constant, the thing that is constant is when my program runs, I can say wherever I start from, this is inside of my little walled garden. This is where I'm going to store the data that I need for my program. And that's why this offset, at least here, is always going to be that same number, 406,000. So I'm going to put this here, 406,000. And just to make this easy on myself this time, I'm just going to add 1 to everything here. So I don't have to write it all out. And so now you can see in memory, in real memory, in my offsets, this is where the D is going to go, this is where the E is going to go, and the M and the O, and then the null terminating character is going to go at offset locations 406,004. And so that's setting up this guy here, and now a character. I can use that as a D word. Whenever I have a pointer in my environment, all pointers are 32 bits of storage because it's a memory address. It doesn't matter what the thing is pointing to, a character, an int, a float, a thing that's 1,000 bytes large. What matters is its memory location, and I'm working in a 32-bit architecture environment, so my pointer, my memory address is going to be 32 bits of storage. And I can say, you don't have to put the offset here, But that is what's good here. Offset means, demo is a variable. It would, if I didn't use the offset, it would actually print the capital D. I don't want to get into more details, but by saying offset, basically, you're saying get me the memory address of what demo is and put that into character. So that's doing the same thing as we did in C++. This stores the 406,000 as we were talking about earlier. And I can do that just by saying put character in here. And there's my 406,000. If I get rid of the word offset, does it do the same thing? And the answer is yes. And that's because just the syntax of this, because demo again is a pointer, even though it doesn't look like it, even though all this memory is being stored, demo is still a pointer to where the thing is in storage. It's interesting, right? It's just the way things go. Okay, so I'm going to use the offset demo here. All right, make sure one more time, because as I'm talking and doing, I'm doing less thinking. And there we go. Okay, so I have my two variables set up like I had before. And now we can go through the code. Okay, I'm going to start with the loop itself and say local variables are covered later in the semester, right near the end of the term. But I'm trying to tell you that all I'm trying to do is get you to use a move instruction to put 4 into the ECX register. And ECX is a full 32-bit register, and I need that for the while part of this do while loop. And I need a label. Whenever I have a loop, this is trying to scream out to you to use the loop instruction, because remember, go back to your notes, that the loop instruction decrements ECX register and then checks to see if it is 0. And if it's not, then it goes back up and loops again. Otherwise, if it is 0, it falls through. So this is what I'm trying to get across here, right there. I'm trying to say, okay, set ECX to 4 outside of the loop. Here is where you come back, again, when you do another iteration of the loop, that opening curly brace, basically, if you want to think of it that way, go through and loop again, loop again. And I can show you that this works this way if I go and I call right int here. And I run this as such, you can see that I get 4, 3, 2, 1. That all prints out like because I'm doing this loop 4 times, and that's what we're going to do. We're just going to change up and print out each character instead of a number here. Okay, so that is working for us. And then down below here, I just have to call CRLF for control, carriage return line feed, and then system pause is a call wait message. Just trying to do, and then the exit, there's technically no return value. I guess you could move 0 into EAX. You could do whatever you need to do to exit out of your program. So just to say, this finishes everything up nicely here, and this is what you get here now. And so I can get rid of this, and we're ready to finish up the last 2 steps. And so it gets a little tricky, especially if you haven't dealt with pointers, raw pointers before, and raw memory addresses and things like that. It can get a little tricky here. But let's take a look here. So I want to print out star character. So if oh my goodness, all that crazy stuff, because character again is storing a number. It's not storing the actual D that's stored in memory. So I have to dereference that before I do a print statement. And even something like this takes 2 lines of code in assembly language. Something as simple as, or just to get the value that's stored at star character, it really is 2 lines of code. Because I have to go to 406, then I got to dereference, then I got to get the value. Especially the way things go here. I have to say, move into AL register. I could just try it just to show you here, and I could say byte pointer character, and I can do star. Maybe I can do this. Can I do this? Get an error? I can't tell. Okay, it succeeded. Maybe I don't need 2. Sometimes I do need 2 lines of code, and sometimes I don't. And then what happens if I call write here? See, that's the thing. Nothing printed out. Even though you're like, okay, go to character, dereference it, treat it like a byte, and all this fancy stuff, and like nothing truly happens, nothing prints out. So what I'm going to do here is I'm going to do 2 lines of code. I'm going to move character, and I'm just going to move it in here. And then I'm going to say move into the AL register a byte pointer of EAX dereferenced, and try this again. And now you will see it prints out D 4 times, right? This is black magic at this point, right? You're like, what in the world is going on? And what's happening here is, what I'm doing is I'm moving character into the EAX register, because there's a difference between accessing a register versus accessing memory. Accessing memory takes the entire operation itself, apparently here. Accessing the register does not, because the register is on the CPU, so no extra work has to be done to get that information. And so please correct me if I'm wrong with this stuff. Anybody correct me in the comments and I will redo the video. But that's my understanding of it. So in order to dereference, I have to move the memory location from memory, because that's where this is stored, right? This is stored in RAM. Move it onto the CPU, so then I can say, okay, now dereference this thing, and I can do this because I can't do it in 2 lines of code. We just showed that it doesn't work if I just go ahead and I take this and I byte pointer it. And so what this means is, now that character is 406,000, it's stored in the EAX register. Now I can say, okay, go to that memory location, treat the pointer, basically static cast it from an integer pointer to a byte pointer. So I only access the information stored in this 1 byte at 400,000 or 406,000, and get me the 1 byte and put it into the AL register, and then print that thing out. And that's where the D comes from. And then loop again, loop again, loop again, loop again. Again, we've proven that we do this 4 times. And so the only thing left to do is the whole code here is to increment character. You do not want to increment demo. I don't even know if you can technically, because it's sitting under the hood as a pointer. But now it should print everything we're expecting to. And now it prints demo, DEMO, for the same reasons as it did earlier, because this is the hard work, 2 lines of code to do the 1 print statement, or 3 lines of code if you want to think about it, to do the 1 line of code. But under the hood here, I've got 4 in the ECX register. I've got 406,000. I go, okay, go there, put it into the AL register, or EAX register, put the whole memory, and then dereference, put it into AL, and then print out the D. Oh my goodness, right? And then increment character. So this becomes 406,001. Decrement ECX. Is it 0? Nope. Come back around. Move this value into the EAX register. Dereference this so I can just get the E. Print that out. Increment character. Decrement ECX. Are you 0? Nope. Do it again. So go to this memory location. Get me this 1 byte. Print it out. Increment character, decrement ECX. Are you 0 yet? Nope. Well, we're almost there. Okay, so go to this memory location, do the work to get me the O, print out the O, increment this guy, decrement this guy. Are you 0? Yes. Program ends, right? And it falls through CRLF wait message, and everybody's happy. And now things to notice. This character pointer has been completely blown out. It's pointing to this right here. It's not pointing to the D anymore. It is pointing to the null terminating character. And ECX will always be basically blown out as well. The 4 that started has now been replaced with a 0 when I fall through, because that's the only way out. So you have to understand that we modified, to do all this work, we modified a variable, and we modified the register under the hood, but we got the output that we were expecting. So this pretty much covers, everything that needs to go in this example here. Let me see if I can get everything onto the screen in one go here. There we go. And that's how you would do it in, just break this up a little bit here. This is how you would get everything going in x86 assembly language. Not meant to be a ton of code, but this, especially with byte pointer, all these things that you're not accustomed to, that one line of code can be a pain in the butt to get moving. So I hope this was a helpful demonstration for you. If not, you can get a hold of me at swardb@cud.edu and let me know. Please be kind. You can get a hold of me here on the comments. You could let me know what other kinds of videos you'd like to see, because at this point, I'm doing my best to fill in the gaps that the last year has, that we've seen in the last year with student understanding in the online environment. So I'd love to hear from you guys to see what I can do to, to make things better. So as always, thanks for sticking it out with me. Have a great day, everyone, and we'll see you next time.